Hello. Anyway, we have a quiz today, so we're just gonna do quick stuff. As you can see from the title, hopefully, we're gonna talk about protein structure, enzymes, and coenzymes. I feel like I should do just enzymes and coenzymes, but whatever. Let's just like skim through proteins. Okay, so proteins are usually This video is not sponsored by Adidas or anyone, but this is definitely made for self-revision purposes only. So that means any examples I use might or might not be scientific. I am too tired to actually explain which ones are and which ones aren't. As you can clearly see that I'm studying like a few hours before my quiz, okay? And I had like all week. So, proteins can be of two types. What are they? Fibrous and globular. Fibrous and globular. Okay? So, these, okay, I'm gonna draw this. Imagine this. Muscle fiber, globular, globular. Okay? I'm just gonna skim through these. Okay. I'm just gonna like tell you the fibrous proteins, collagen, okay, and tendons and stuff. And globular protein being like soluble in water, mobile within cells, right? And fibrous ones are polypeptide chains arranged side by side in long filaments, which are tough and insoluble in water. So collagen, maybe cellulose, these type of shit. I don't think cellulose is no, it's not a protein. This globular, spherical inside the cell. So in your own world, be with the world. Water. It's where, yeah. So let's talk about the structures, okay? So proteins, this is like the type. This is the type, okay? Now let's talk about the structures. Yeah, of course, be that, yeah. Just when I have to be like in a rush and something, right? Anyway, so for our protein structures, we got 4 categories, okay? I mean, these are like easy stuff, you can do it. Primary, secondary, tertiary, quaternary. Quaternary. I'm not sure about the R here, but so these are like the possible protein structure types, right? Actually, not possible. This is how it goes, okay? So it's like this part is your chain, amino acid sequence, right? Like amino acid, it's like a chain, right? This part is when the chain, and I'm just gonna color this so it's easier for you to understand. This chain folds, okay? Okay, see this is how it folded, right? Like you should zoom into this, but yeah, whatever. This is when like it folds into like a shape. I don't know how any of this is called a shape, but you get this thing. Like it's like, imagine we cut like a strand from here, and this is the one, right? And then quaternary is this like one polypeptide interaction with the other. And this is your quaternary structure, right? So this is like the last structure, like so far as my knowledge. And then you like break this, and then it forms this, and then you take the strand, this is it, and when you zoom into the strand, this is what you get. Easy. This has like no types, like you're just like coding the amino acid, right? Point by point. But this, it's got 2 types: alpha helix and beta weighted sheet. So alpha helix is practically, this is what it looks like. Like, see the helix, like those dramatic staircases. Yeah, this is what you're going for. And beta pleated sheet, this is just like, let me just get the paper for you to understand. This is pretty much this, okay? See the bonds in here, right? This is what causes a beta pleated sheet, right? Whereas, why did I remove that? Okay, you see like the bonds which possibly might be going on here. This is alpha helix. Do we need an example for alpha helix? No, but we do need this thing. Okay, so alpha helix. Wait for it. Okay, so this is my alpha helix. I know I've done a terrible job of drawing it, but just bear with me, all right? So these amino acids, so like 1, 2, 3, and 4. No, sorry. 1. Like after this one, there's another 1, 2, 3, And then your fourth amino acid, it's gonna like form the alpha helix structure, right? So that means that the first amino acid forms the alpha helix thing. I'll get there. Alpha helix thing with 4 residues away from the, like 4 residues away from the, okay. Let me explain to you like this. Imagine this as a sequence: glycine, alanine, what else is there? Isoleucine, leucine. Then we got 1, 2, 3, 4, 5. Then I'm just gonna continue here. Leucine. I'm gonna do phenylalanine, right? So you see, I hope that is visible. Yeah, that is visible. Okay, so you see, this is 1, 2. Oh no, we're gonna make this one. Okay, so we're just gonna call it 0. I'm just gonna call it 0. This is not what they're called. 1, 2, 3, 4. So you see 4 residues away. It's gonna form the bond all the way from here to here to phenylalanine. Okay, not with these 4. The one, like the 5th one. Okay, and the reason it's easier for it to do is because this thing reverses. Like it goes. Let me draw it again. It goes like this. Phenylalanine, right? And then it continues on. So you see how it's doing its thing? So let's do it again. 1, 2, 3, 4, 5. So this thing will form, what color did I use? Okay, red. Hydrogen bonds. These are hydrogen bonds that is used here. Okay, H bonds. Now how are these H bonds formed? So I'm going to drop 2 amino acids quick for you to understand. I know I've like dropped what's super small in there. Should have made better decisions. Oh, whatever. So we got this. I'm just gonna drop 2 for the easy way of understanding. Okay, NH3 plus R. Oh wow, I literally forgot how to draw an amino acid. Okay, this thing, and this is whoa. And then we're gonna do another here. Okay, now this time I'm gonna reverse it so it's easier for you to understand. But you see the structure at the end of the day, it's same. Right? So you see this O here will form hydrogen bonds with this. Right? And what is the distance between them, people? What is the distance between them? Even I don't know, so we're just gonna look at the book. 2.8 angstrom. That means 280 ppm. Okay, yeah, this is the one I used. 2.8 angstrom. And 2.8 angstrom also means 280 ppm. I hope you can see that. Yeah, you can see that. Achha. So this is the one, and for the carbons, okay, like the alpha carbons here, this is an alpha carbon, this is an alpha carbon, right? What is the distance between the alpha carbons? The distance between, wow, this looks horrible. The distance between the alpha carbons, okay, so let's do this, is 540 ppm or 5.4 angstrom. I think this is what angstrom is actually called. Clear. This is alpha helix. We talked about alpha helix. What is an example of an alpha helix? Myoglobin with 153 amino acid residue in a single chain. We're going to be coming back with beta sheets. Okay, for our beta ones, okay, beta sheets, okay, I'm just going to use this. Okay, I know I haven't drawn it like properly, but like just bear with me, okay? So you see how... Oh, this is my peptide chain 1. This is my peptide chain 1 and this thing, and this is my peptide chain 2, right? So you see how this amine part is like hydrogen bonding with the carboxyl of this like peptide chain 2. That's it. That's beta. This thing is straight, right? But that thing was coiled. Now beta sheets are more common like in peptide bonds, right? The neighboring chains can run either in the same direction. Okay, so like they're both moving like in this direction, or they can just move in opposite directions, right? So yeah, that could happen. On top, okay, beta sheets are more energetically favorable. Why? Because oh yeah, this is why they occur more in, you know, like more peptide stuff, right? I need to stop saying right. Okay, one of the examples of this is concanavalin, which consists of 2 identical chains of 237 residues with an extensive regions of anti-parallel beta sheets. Oh, sorry, anti-parallels are more common because they're more energetically favorable. So let's just say one chain goes this way and the other chain goes this way, right? Easier way to remember this is that opposites attract likes, repelled, right? So this is more energetically favorable because they attract more. They repel more, hence they're not energetically favorable. So yeah, anti-parallel thing, anti-parallel, yeah, running in the adjacent chain, it's that. Okay, whatever. That was beta pleated sheets. Now we're gonna talk about tertiary. So before we do tertiary, I need to tell you about a few stuff, like a few forces that we've learned very much as a kid, how they affect tertiary structures. Okay, so there are a few kinds of forces we're going to talk about. Let me read them. Even though during my A-levels I've studied like so many, there were like 5 things I think. This book says that there are 3. So I'm going to just go with my instinct, which is I'm just going to start writing and I don't know. So we got hydrophilic, hydrophobic, salt bridge, which I think can also be called ionic interactions. Okay? So remember, this is like, your chain, your secondary structure, right? And then, all of this just folding into a compact thing and then making like a shape. So this is your tertiary structure. Just like a quick reminder. Acha? So hydrophilic, feline. People, what is feline? Feline. Philic is feline. Feline are cats. People like cats. I don't. People like cats. Everybody loves cats. I'm sorry, I'm more of a horse person. Yeah, I'm Caroline Channing from Two Broke Girls, but whatever. Feline. People like feline. Hydro, not hydro from Captain America. Hydro is water. So hydrophilic. Feline. Water plus cat. I like. Cats don't like. I like to see them suffer. Why? I don't know. So, hydrophilic interactions. Who do these hydrophilic interactions be happening to? Ionic stuff, I believe. Okay? And then we have hydrophobic. Phobia. Hydro. Water, afraid. Oil. Hydrophobic interactions be causing tertiary structures as well as hydrophilic. Salt bridges. Now this is fun. Kudos to my chemistry teacher from A2 who explained this stuff so good that I forgot. But honestly speaking, he was one of the best teachers I had. Anyway, presence of ionic attractions between positively and negatively charged sites. Girl, the definition says it all. It's like this. I know I'm not sure if this is correct. Just bear with me, alright? This. With maybe this. Right? Makes sense. So these are the 3 things which be causing the tertiary, like which be giving you the shape. So like the fact that you like seeing, cats like, play with water, and the fact that you're maybe scared of water yourself, and the fact that you're a salty, right? All of this will shape you and shape your identity. Remember that. Period. So tertiary structure, we're not going to talk about quaternary structure because honestly it's not in my syllabus right now, so I'm just not gonna, and you or me, so girl, we just gotta raw dog this stuff, right? So tertiary structure. Okay, so what happens, most enzymes are proteins, or maybe all enzymes, not so sure, but as far as I know, most enzymes are, right? So now, how we've heard that, enzymes get denatured, blah blah. It's like, how your food gets stale, how you get diarrhea, all that crap. It's all because of enzyme denaturation. Okay, so imagine you had such a good meal. Okay, like you had like 13 crabs. Not speaking from IRL examples, but whatever. So you had 13 crabs because I don't know, you were like competing with your cousins, right? Now you've had that, and it's like super hot out, right? And even though you've had that, and you feel pretty full, and you don't feel like really throwing up, but after a while, because it's so dang hot, you feel like throwing up. Why? I cannot do that. But anyway, it's because, your stomachs, it's got enzymes like pepsin, chymotrypsin, I think, but whatever. Okay, pepsin, we'll talk about pepsin, okay? Pepsin, instead of digesting your enzymes, digesting your crabs, I don't know if pepsin is the one which digests your crabs, so just bear with me, okay? Instead of digesting your crabs, it just didn't, because it went raw. Sorry, why would it go raw? It went rotten, right? Now, why would it go rotten? It's because it got denatured. Now, what is denaturation? It's because it just stopped working. Why would it just stop working? It's because it's lost its shape. Oh wait, isn't enzyme a protein? So if it lost its shape, what does it mean? It means that it's lost its tertiary structure. How does someone lose the tertiary structure? Despite having, I don't know, hydrophilic, hydrophobic, and salt bridges interactions. I'm glad you asked. Now, remember, to break forces, what do we need? Heat. Okay? I mean, this is the reason. I mean, you did end up, like, I don't know, throwing up your crab. PTSD activated. You did end up throwing up your crab because, I don't know, it was really hot outside. So hence heat. So heat does denaturation. How does denaturation work? It works in both physical changes and biological properties changes. Okay, so that means your solubility is decreased. Okay, so I don't know, when you get hot, you stop, like, I don't know, socializing with, like, other people. So you stop being soluble with other people. Like, I've seen people do that. So, like, yeah, whatever. So yeah, solubility is drastically decreased. So most enzymes lose their catalytic activity when denatured, since a precisely defined tertiary structures is required for their action. And most denaturation is irreversible. Some of them are spontaneous. Renaturation of unfolded protein to its stable tertiary structure occurs accompanied by a full recovery of biological activity. Pretty sure that went over your head because it sort of did to mine too, or whatever. Listen, okay? So denaturation, it undoes the tertiary thing, right? It might undo the secondary thing, you know, the one that folds, but it cannot undo the primary structure, like the sequence. It cannot break the amino acid sequence normally, okay? Normally, it cannot. It loses tertiary structure, and the reason the tertiary structure, okay, like the breaking of tertiary structure, like the losing its shape, causes it to, like, not work, is because, I mean, to click with people at the end of the day, you still like need your personality. You know, if your personality kind of like just changes its shape just because you got hot, girl, you need to stop watching my videos then. But whatever. Yeah, that is that. Usually, if a person gets hot and they change shape, it's kind of irreversible for them, right? Because, I mean, ego involved, you know, all that Judaiya involved, whatever. But in some cases, it is reversible. Now, in that case, we call renaturation, okay, which just like reverts back its full biological activity. I still don't know how that works, but let's get on with it, right? Now we're going to talk about enzymes and coenzymes, right? We just talked about denaturation, structures. Now we're just going to talk about enzymes and coenzymes. What are enzymes? We've learned it, girl. We've learned it. What are enzymes? These are like catalysts, biological catalysts that work in a reaction, but they don't get used up. How do they work? They work by lowering the energy needed for the reaction to happen, as in the activation energy, right? So just to explain, okay? So it's like, you know, if I did this video and a couple of other videos, you know, all of them, which are right now needed for my quiz, okay, if I did all of them together in one day, I would need a lot of energy. Seriously, okay? But if I did them, like, you know, like how I made one video yesterday, the other one last week, the other one, like, other day, right? Now, all of it, you know, my knowledge, it seems like a little easier for me to carry. Genius. Anyway, it's easier for me to carry, and it's requiring less energy for me to remember because, girl, I yap about a lot, right? So it's like that. I feel like I should just draw it. I can't believe I have to draw it. So this is my energy pathway thing. So this is how reaction progress, and energy, right? So when the thing is uncatalyzed, so you gotta study for everything in one day. That is harder. That requires a lot of energy, right? But imagine if you just like studied step by step, right? See how this makes it easier? Wait, hold on. I need a little space. So it's still gonna have like the same starting and ending point, as you can see. Starting and ending point, as you can see. So this is what an enzyme does, right? Now, let's talk about parts of an enzyme, right? So the enzyme is usually a protein. Oh, right, it does not participate in the reaction. So it's like, you know, the friend who knows all the dramas, you know? It's like a key player in the drama, but she's really not part of the drama. Let me tell you a story. This one time, okay, one of my friends, we're gonna call her T, okay, told me how this guy, okay, also her friend, okay, S, okay, S had an interaction with our mutual friend, like T's and I mutual friend, A. I feel like I should, okay, Tiffany once told me about an interaction that Samantha had with Aisha. Right? So So, I wasn't technically supposed to know that, right? But one day I was joking about A with it, right? And A was like I ended up just like was like, dude, that was like a fun interaction. And then A went to Samantha and she was like, Samantha, did you just like spill our combo with like Tiffany? And then like Tiffany and Samantha, they started freaking out because like, how did it get out? And then as it turns out, I was the one who got it out. And then I had to like come up with a story that Tiffany, like, I jokingly like, no, okay, Tiffany jokingly said that to me, and yeah, well, it was this whole thing. So you see, like a whole fight broke out because of me, and I wasn't even part of the thing, right? I'm the enzyme. Okay, I caused the reaction. I mean, that fight would have happened, but it was catalyzed because of me. So you get it, right? You get it. You get it. It's clocking to you. It's clocking to you. I feel like it's clocking to you. Okay. It only lowers. So activation energy is lowered. Activating energy. Activation energy. Okay. So enzyme has two parts usually, as it says in this book. Wow, did I like not read that? Okay, two parts, which is like a protein and then a cofactor. Okay. So what is it? We know the protein part. Okay, and the cofactor is usually an inorganic molecule or like a small organic molecule. So now let me tell you the story. Okay. So I have iron deficiency. Big deal? Nah. Okay, but a little fatal. Okay, whatever. So so the reason, okay, I'll be having like a lot of protein in my diet, right? But like I'll be immediately having caffeine after it. Okay, and I'm talking about like months before. Okay, and my father was like, yo, that's not cool because like what you're doing is that, okay, so you are taking in your proteins and you know your irons, is in like, you know, proteins and irons. Okay, so what's happening is that when you're taking in your caffeine, okay, it's reacting with the iron, making it useless, so only your protein's there. And you're gonna learn about it, and I have learned about it, is that without the inorganic part, without the cofactor, okay, like this little iron, okay, the protein is kind of useless. If this isn't correct, please go ahead, charge my teacher, I will give you her address. But yeah, you get it? Okay, so when it's not an inorganic inorganic ion, the cofactor, when it's a small organic molecule, it's called a coenzyme. Okay, now I'll be discussing a few enzymes, proteins, like, oh right, sorry, oh right, okay, so the coenzymes usually come from vitamins. Now in case you forgot what vitamins is, come on, can you really forget what vitamins is? But I just want to say the definition, but whatever. It's substances that an organism requires in small amounts for growth, but is unable to synthesize and must receive in its diet. That reminds me, I should probably get some vitamin C. I need my skin to glow. But whatever. So many coenzymes are derived from vitamins. Now I'll be like writing a list here, and just bear with me because my grandma's old perfume, which smells really weird, just ran out. So I'll have to figure out some weird way to just erase this, so it looks at least clean. So okay, we're back. Somehow water worked. Sometimes it doesn't. So. Anyway, so I've written like the complicated vitamin names here, along with the easy ones here. Which ones have the easy ones, right? So, okay. So let's talk. Okay, vitamin B, also known as pantothenate, pantothenate. Vitamin B. It's for your hair. I know. Pantothenate or vitamin B gives our coenzyme A. Coenzyme A. Where did we learn that? Glycolysis, I think. I don't know. I cannot make a connection. I cannot make a connection between glycolysis and keratin. So just like bear with me, alright? Vitamin B gives coenzyme A. Niacin gives NAD+. Niacin. Niacin. I don't know what niacin is, but yeah. Riboflavin. I feel like we've heard this like a lot. Also known as vitamin B2 gives pyroxydyl phosphate. Now for like the ease of you and me, we're practically the same person, and I'm just gonna write it as, oh my god, P. Pyroxydyl P. Vitamin B2 gives pyroxydyl P. Folic acid. We'll all taken, I think, folic acid. It gives tetrahydrofolate. Okay, follicles, folic acid, tetrahydrofolate. I don't know if it's follicle related, but just bear with me, right? Thiamine, also known as vitamin B1, gives thiamine diphosphate. This is your list. Okay, now I'll be talking about enzyme categories. Should have made 2 videos, people. Should have made 2 videos. Because I always try to keep my videos under 30 minutes. But whatever. Let's talk about the 6 categories of enzymes. As you can see from above my head, okay? So the black ones are the classes, okay? And the blue ones are the subclasses, okay? So now let's talk about it while I flash you with my hair. Anyway, so what are the classes of enzymes? We go oxyreductase, transferase, hydrolase, oxireductase, transferase, hydrolase, lyase, isomerase, ligase. Okay, so OTH lil. So there are subclasses. The subclasses of oxireductases being deoxyhydrogenase. What does deoxyhydrogenase, oxidase, and reductase. Deoxyhydrogenase. Oh no, it's dehydrogenase. Dehydro. Oh, I am gross. I am stupid. If you know that, you're a cool one. Dehydrogenase. Okay, dehydrogenase. So what does dehydrogenase do? Dehydrogenase. Okay, now before we talk about the subclasses, let's talk about the classes. Oxidoreductase catalyzes the oxidations and reductions. Okay, while its subclasses, dehydrogenase, it introduces double bonds. Oxidase does the oxidation catalyzation, and reductase does the reduction catalyzation. So this is more than enough for you to understand. Then we got transferase. What are transferase? They catalyze the transfer of a group from one substrate to another. Okay, so the subclasses that we have are kinase and transaminase. So kinase, they transfer phosphate group, whereas transaminase, they do the amino group. Okay, hydrolase, they catalyze the hydrolysis reaction of esters, amines, and other related substrates. Okay, we know what that is. We've done hydrolysis. So the types of them are lipase. So this does ester. Nuclease, which does phosphate. So you know how nucleic acid has a phosphate backbone? This is your stuff. And then protease, amide. So proteins, as we studied before, it's got amide bonds, right? So can you see it? Yeah, you can see it. Or we might want to switch to some other color, which is red. Now where is the red? Yep. Amide bond. Okay. Then we got lyase, catalyzes the elimination of or addition of small molecules such as H2O from or to substrate. What are the examples? Decarboxylase, loss of carbon dioxide. Dehydrase, I believe it's loss of H2O. Yes, loss of H2O. Isomerase is the catalyzing isomerization. So the subclass of it is epimerase, which isomerization of chiral centers. Okay. Then we got ligase. Ligase catalyzes the bonding of two molecules, often coupled with hydrolysis of ATP. The subclasses being carboxylase plus carbon dioxide, and synthase, new bond formation. So I want to say this is the stuff, but we're still not done. We still haven't covered the peptide thing, right? I will give you one example. Okay. Now remember this this graph that we did, for like catalyzed and uncatalyzed thing, like the energy graph. Okay, so I'm just gonna redraw that real quick for you to understand. Remember how we did like step by step? Okay, so what was here again? Here was energy, here was reaction pathway. Sorry for the handwriting, but none can do. So this is my uncatalyzed. Okay, and I'm just gonna do my catalyzed with red this time because the green one is somehow not working. We did this, right? Go higher, lower. This. Catalyzed, and uncatalyzed. Right? Now, as you can see, like these little steps. Okay, so how does an enzyme work? Now we're gonna talk about how an enzyme works. How does it work? Is that enzyme, okay, I know we said it doesn't react with the thing, but just bear with me, okay? It reacts with your reactant. Okay, so this is my enzyme. Okay. I feel like this should be like this. Okay. This is my enzyme, and this is my reactant. Sorry. This is my reactant. Okay. So we kind of want this reaction to happen. This is my product. This is my reactant 2. Okay? And I feel like this is a really bad diagram, but just bear with me. Reactant 1, and this is my enzyme, right? So what really happens is that this comes here, okay, binds with this, forming ES. What is ES? This is ES intermediate. This is enzyme substrate intermediate, okay? So you see how now this can easily fit into this, okay? And this happens, okay? And I don't know, with some magic, okay? Then we like this transforms into my product, well, gross. My product, which is, I need pink, which is this pink thing, okay? With like our enzyme attached, our enzyme attached, right? So it's gonna be something like this, right? I think my enzyme looks something like this. This is my enzyme, and this is, the pink thing is my product, right? You can see it, right? So we don't need the enzyme. We need to get rid of the enzyme. So this thing right now is called EP intermediate, as an enzyme product intermediate, okay? And now, finally, we're gonna get this. This with this. It somehow just got separated, okay? I know it was like a really bad diagram. This is the last thing, right? So this is how an enzyme works. So I'm just gonna do like a quick enzyme plus substrate, my reactant. Okay, then we have enzyme substrate complex, then we have enzyme product complex, and then we have enzyme plus product separately. Make sense? Makes sense. Another term I need you to remember is that turnover number. It is the overall rate constant for conversion of ES to EP. Okay, then it represents the number of substrate molecules in a single enzyme turns over to product per unit time. So yeah, I mean it's just like ES complex to EP. Okay, so this relation right here in the green thing, this is your turnover number, like the amount of time it takes for this to happen. Okay, so there's that. Some factors which accelerate enzyme activity is the shape of the enzyme, tertiary structure, guys. Remember, shape of the enzyme and the whole. So you know these I think are called transition states. Okay, like it's transitioning, right? So transition state. So you know like the kind of environment an enzyme creates during the transitioning state, that somehow just like lowers the activation energy. Now, this is why I wanted to draw this again. You see this? EP and E plus E. This is how this thing is drawn. Get it? Now, one thing, I want to give you one example of a globular protein, which is papain. Now, I'm glad you asked what a papain is. It is used in contact lens solution and the very skincare I first learned, which is this. You can see it, but like, see papain? It says papain. I'm so proud because I'm actually studying the stuff that's in my skincare. So yeah, there's that. So papain. What does it do is when you get like a big ass peptide, you react it with papain and H2O. So papain, when it reacts with when we add, like imagine there's like big ass polypeptide, right? And so when we put that in like a solution of like water and papain, okay, it just like breaks the amide bond. The peptide bond, it hydrolyzes the peptide bond, which makes it a good cleaner for contact lenses. Another thing I forgot, oh wow, we are all over the place today, aren't we? Is that how you name enzymes? Okay, so enzymes usually they got like two parts. Okay, so one part is the substrate. Substrate, it catalyzes. The other is the type. So it could be, the other type could be like something oxyreductase. Something being substrate. Get it? Best of luck for your exams. Still need to study. Bye.